All right, so let's go ahead and find power series representation of a function centered at x naught. So suppose you have some function f of x, and you want to write this as a power series. So you want to express s as the infinite sum starting from n equals 0 to infinity of some cn times x minus x naught to the n power. Now, since I'm going to be working on centered at 0, my x naught is 0, so this piece will disappear. So you'll just have x to the power of n. I'm choosing specifically the center to be 0. So we want to do that for the following function. So let's take a look at this function. So say f of x is equal to tangent inverse of x. And I want to write this as a power series. So n equals from 0 to infinity of what goes in there. So we want to write it that way. So the idea that we're going to use is a differentiation and integration. That's one way we can express the power series representation of tangent inverse of x. So let's go ahead and do that. So we're going to be using some calculus technique. So at this point, we're all very good at differentiation. So this should be the fun part. So let's go ahead and differentiate f. So if I take the derivative, I'm going to call this as another function. So I'm going to let f prime of x be the function g of x. And we know that the derivative of tangent inverse of x is 1 over 1 plus x squared. So I'm just calling another function, g of x. Doesn't really matter. Now, my goal is to write this in the following form because something we know about this. You want to write this in this form. So express it as some a over 1 minus r, because that's the form that a geometric series converges to. So if you can write it in that form, this can be written as the sum from n equals 0 to infinity of x to the n. And we know this converges. So instead of r, of course, I'm going to replace it with x. So I'm going to write it in that form. And also the a, I want to make sure that's also 1. And which is what we have really in this form. So if I can write it that way, then I know it could be written as the infinite sum of the geometric series. So that's the goal here. So we also know that this will converge as long as absolute value of x is less than 1. So it gives us more information if we can write it in this particular form right here. So that's what I'm going to do here. 1 over 1 plus x squared. We're going to play around with it. And we can say, okay, this can be written as 1 over 1 minus x squared. Exactly how we want it. So then this is your x, or r, if you want to think of it that way. Then this can be written as the infinite sum starting from 0 to infinity of a is 1, so it'll be x negative x squared to the n power. So that is your power series expression of this function 1 over 1 plus x squared. Let's clear things up. So we know that this function g of x, which is 1 over 1 plus x squared, can be expressed as a power series as this form, this sum starting from 0 to infinity. We have negative 1 to the n times x to the power of 2n. So that is your g of x. Well, now we don't want g, right? We want to go back to f. So that means I'm going to integrate this function because that's the derivative of f. So if I integrate, I go back to my original function. So I'm going to go ahead and integrate this. So if I integrate g of x with respect to x, so I'm integrating this function, this infinite sum, respect to x. So this is what we get, negative 1 to the n times x to the power 2n dx. Now let's keep in mind that this series will also converge same as this one. So we know that the interval of convergence for this series is also an absolute value of x less than 1. So I can integrate within this convergence, the interval of convergence. So I can do the following. I can look at the sum from 0 to infinity of the integral of negative 1 to the n x to the 2n dx. So I can do this switch because I'm integrating only within that interval, negative 1 to 1, because that's where the series converges. All right, so let's proceed with the integration. So we know this is our function f of x, because if you integrate g, which is f prime, you get f of x, which is tangent inverse. So we know that the tangent inverse of x is equal to the infinite sum from n equals 0 to infinity. Integral of this, well, -1 to the n, that's just a constant. So keep the constant and integrate x to the 2n using power rule of integration. So this will be x to the 2n plus 1, and we also put same power on the denominator, plus c. Don't forget the integration constant plus c. So we're able to express tangent inverse as an infinite sum or as a power series, except that there's a plus c next to it. So how do we solve for c? Well, I can plug in where the series was centered at, which was at 0. So if I plug in x equals 0, I have tangent inverse of 0 is equal to, when you plug in 0 here, x 0 to the any power is going to be 0. Summing of infinite terms of 0, that's going to be 0. So you have 0 plus c, so c is equal to tangent inverse of 0, which means tangent inverse of 0 is 0, so we know c is equal to 0. So our final answer, we're able to express tangent inverse as a power series centered at 0 as this, and from 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1. And this will converge the absolute value of x less than 1. Now you can test the endpoint to see if it will converge at the endpoint. This will converge one of the endpoints. You can test that by using ratio test. You'll see that this will converge at 1, but it will not converge at -1. So this is the interval of convergence for tangent inverse of x. So there you have it. We are able to express tangent inverse as a power series. Now let's go ahead and take a look at another problem very similar to this, so you get used to playing around with this idea. So what would be the power series representation of tangent inverse of x squared? So how do you write this as an infinite sum? Well, so the idea is pretty straightforward actually. Well, we know what is tangent inverse of x is in power series. So instead of x, we're replacing it with x squared. So all I'm going to do, I'm going to replace my infinite sum where I see x with x squared. So the input, the x will replace with x squared. So you can write this as the sum n equals 0 to infinity of -1 to the n times, so instead of x, I'm replacing it with x squared to the power 2n plus 1 over 2n plus 1. And that's pretty much it. So now we can simplify this a little bit further. So we can say that this is really going to simplify to the sum from 0 to infinity of -1 to the n times x squared. So by laws of exponents, you'll get x to the 4n plus 2 over 2n plus 1. So I just multiply these exponents right there. So there you have another power series representation of this function. This is tangent inverse of x squared. So once you know one function, you can modify it and play around with it. All right, let's try one last example. Let's find the power series representation of x squared times tangent inverse of x. So how can I write this as an infinite sum? Right, so that's what we want to know. Well, we know what this is. We just derived a few minutes ago above. So let's substitute that in there. So we know that this can be written as x squared times the power series representation of tangent inverse, which is the sum from starting from 0 to infinity of -1 to the n power times x to the 2n plus 1 over 2n plus 1. So we just did that. Now, we're just going to go ahead and push this inside the summation. So then this will give us the sum starting from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 times x squared all over 2n plus 1. And here, by laws of exponents, these guys, you can add up their exponents. So you'll have the sum starting from n equals 0 to infinity of -1 to the n times x to the 2n plus, so 1 and 2, that'll make it a 3 all over 2n plus 1. So there you have your power series representation of this function. So once you know one of the p's as a power series, then just play around with it, because this summation belongs to n, so you can push x inside, or if you have a constant, you can also push that inside the summation. All right, so I hope this helps.